It's called NYTC, and it's called Not Your Teacher's Coin. And it uses proof of work as a civil attack resistance mechanism, and it uses longest chain consensus algorithm, just like Bitcoin. And the proof of work is very similar to the Bitcoin, but of course, the difficulty is much less. That means the difficulty number is much higher, and you can use your own computer and coin it, and create a coin, or I should say, win the lottery of proof of work very quickly, within a few seconds. So let's explain how the mining process works. Basically, all of the things that you see here have been developed in the hosted Python code. This is the Python code. Everything that you see in the description is already implemented. The only ones that are not implemented are the ones that are in the tasks 1, 2, 3. And task 1 is basically asking you to run this, so that's not a special task. Mostly 2 and 3. All right. Let's do it. Let's start with proof of work. For distribution of NYTCs in a decentralized fashion, and in order to incentivize miners who want to compile different transactions into blocks of a blockchain, each miner basically goes through a few steps, as you see these steps, in order to basically propose a new block that is made of multiple transactions and a few other items, which we'll talk about them later when I talk about the block data structure. And in order to incentivize the miner will win 8 coins for every successful mining of a block. So let's see how the steps of mining work. Step 1, it picks a set of recent pending transaction from a global list called transaction pool. While I'm explaining, I'm going to show you the code as well. So where is the pool of transactions? Here it is. That's a deck. For those of you who don't know what deck is, that's basically like a list, but it simulates a queue. Basically, you can add to the end of the deck and then remove from the beginning of the deck. So that's kind of like a linked list in Java, but it basically simulates a queue. Yeah, thank you. Double-ended queue. All right, so that's called a transaction pool, and because it's a global list and you have multiple miners and each miner is a thread, transaction pool is prone to get corrupted because of race conditions. So we will have a lock for it. That's called the transaction lock, which you see here. These are minor details. Remember all the details. Then step 2 will make propose. That's the first step of a miner, which is picking transactions. Step 2 is making a proposed block containing the picked transactions and a number called nonce, initialized to 0. So the miner will start from 0, use nonce equal to 0, and it basically combines those transactions and the nonce and a few other items into one block. And in the third step, it calculates the hash of the proposed block using SHA-256, the hash of the proposed block. And in step 4, it checks whether the calculated hash is less than a predetermined value called difficulty, which is again given. That's a, let's say, read-only variable that is global, and it's initialized to this value, which is 2 to the power of 239. And then it increments the nonce and goes back if the value, if the hash value is not less than the difficulty. But if the hash value is greater than the difficulty, I'm sorry, if it's greater than difficulty, then it goes to step 2, because that means the mining is not successful. But if the hash value is less than difficulty, then it means that the mining is successful. It goes to step 5. Basically, this is a lottery between all miners. Whoever wins the lottery goes to step 5. In step 5, the miner will receive the prize of the lottery, which is 8 NYTCs, and its balance is increased by 8 million. As you know, the balance is stored as NYTPs, which is a denomination of the coin, which is called not your teacher's pennies. And all the numbers, all the values of transactions are represented using NYTPs, which is the smallest denomination of NYTC. And that means, you know, the miner will receive a prize of 8 million NYTPs. That's the mining process. Who's going to do the mining process? The miner. Who is miner? Miner is represented by a class, and the miner does its operation in a thread, which I'll show you in the code. The class miner is used to represent a miner and contains these information. You have index, which is a non-negative integer to identify the miner. The miners start their indices from 0, 1, 2, 3, 4, all the way to the number of miners. The default value on the number of miners is 5 here. I'm not sure it's 5, or let's find out. Did I say 5 in the code as well, in the assignment as well? Yes, this is the default values. So you have 5 miners, and these are the default value. Difficulty is 1. Shifted to the left 239 times. Okay, yeah. And we have some other values like N, E, and D, which are stored in a miner. Because each miner must have a signature and must have a public key and must have private key, so everyone knows which miner did what, and they can sign their transactions or sign their the different parts of the block, so that, you know, everyone knows that who has done, who has created what, and who has created what transaction. Basically, each miner must have a private and a public key. Because we use RSA 512, we're going to store N, E, and D, which is going to basically represent both private key and public key. Basically, D is the private key and E is the public key, and N is also public. And that's going to be the private public key of the miner. And also balance, which is the number of NYTPs possessed by the miner. So miner is rich, has higher balance, poor miner has less balance. Then you have balance lock, which is a lock that is going to protect the balance against race condition, because later you will see that, you know, the person who wants to enforce a transaction wants to access someone's balance and manipulate the balance. So we need to have a way to basically protect balance against race conditions. So whenever someone wants to change a balance, they have to lock first, then unlock, or they have to acquire the balance lock and then release the lock. So it says, please note that there are 5 miners, which are all stored in a global list called miner. All the global lists are on the top. You can check them out. This is miner list, which is going to contain 5 miners. I have initialized them here. As you see, line 266 to 269, and each miner is basically running a thread with the starting routine of miner run, which is a pretty long function. You may get confused when you read it. I'm going to explain what's going on. It starts with storing the public key in a local variable, and it reads the time from in nanosecond using time ns, and it sets the nonce equal to 0. It creates a mining incentive transaction for the time that's for the day that for the moment that it wins the lottery, and of course the transaction is in its own name. In this function, index is the index of the miner who runs this thread, runs this function. Then it's going to append that mining incentive transaction to the then the next thing it does is it goes through a transaction pool and pulls all the transactions from the pool. Later, you need to implement a transaction fee for every transaction, so you need to update this part, or maybe update some other part of the code, depends on the way you want to implement it. I don't want to force you what to do, but that's what the miner do. The miner will pulls a lot of transactions from the transaction pool, and it's going to start mining. When I say start mining, I mean it proposes a new block with the current nonce, and if the proposed digest is less than difficulty, that means the miner wins the lottery. Otherwise, it has to increment the nonce and has to try again. And every 10th of a second, the miner in this while loop will execute this if statement. In this if statement, we are going to update the proposed block. The reason we gotta update the proposed block is because within the last 10th of a second, we may have new transactions. So we need to update the transaction pool, and we need to update the timestamps as well. So basically, that's why we have this 10th of a second updates. The way it works is basically the miner pulls all the transaction from transaction pool again, and it's basically finds the longest chain and sets that longest chain as the predecessor for the block. And also, let's see, 1 second. Yeah, so that's is that inside this, right? No, sorry. Yes. So as I said, within this updates, we're gonna pull the transactions again. As you see, the transaction gets updated. And one more thing the miner will do is this function. And this function is basically initiates the number of transactions with a certain rate. Because you want to have a lively environment, we're going to ask every miner to donate half of its balance to other miners once in a while. And that donation happens within this initiate transactions. So once in a while, the miner gets, tries to initiate a bunch of transactions for randomly, and basically it wants to get rid of half of its balance by donating it to other miners. That happens here, which I'm going to explain it later. So let's go back to the explanations. Each miner is basically running a thread, as I showed you. It spawned at the beginning of the program, running the proof of work algorithm, making transactions. That's basically the function initiate transactions, and finally joining the main thread after generating 4 new blocks. So why does it say that? Because here in this while loop, I keep counting how many blocks I mined in this thread. If the number of mined blocks reaches to the maximum, which is set to 4 in the starter code, that's equal to 4, then I will stop. I will end my mining because I don't want this simulation to end to keep going forever. So we have to have a stop or end time for it. So basically, after mining 4 blocks, each thread is going to die, and when it dies, the main thread is going to join them. You see this last part when I say where I join, yeah, in line 276 to 77, I join all the threads. So that's the time when all the threads are done mining their blocks. So each thread mines 4 blocks. If you have 5 threads, you have a total of 20 blocks mined. Anyway, so that's this part. Let's go back to the remainder of the assignment. The block structure. That's a very important part of it. That's the part that you will need to enforce the validity. I'm going to explain what each block is. Each block is represented by an object called block class. So the miner class and block class are both available. You can take a look at them. This is the miner class, and the block class was on the top. This is how the block class look like. There's a constructor for it, and there's a string method for it. Let's go over. Let's go over the block. Basically, each block has a set of transactions, a list of transactions. And also, it has pred digest, which is the digest of, or SHA-256 digest of the predecessor block. It has block number, it has block miner index, it has nonce, it has timestamp, it has digest. Transactions is obvious because every block has to have a list of transactions, and these are all pulled from the pool of all transactions. Then you have pred digest. The previous block has a digest. We're just going to store that in the current block. That's the whole idea of blockchain. For the Genesis block, which is the very first block, the pred digest has to be set to 0. And this pred digest is an integer because it's going to be the digest of the SHA-256. It's going to be a 256 binary or 256-bit long binary number, which is about 77-digit integer number. So when you see big numbers, when you run your code, don't get surprised because these are all the actual digest. And you have block number, which is the number of predecessors in the longest chain, including the Genesis block. So the block number of Genesis is 0, then the next one will be 1, 2, 3, 4. And always, in order to find out who's the longest, where the longest chain is, you need to get the maximum block number. That's exactly what I did here. If you go to the miner code, in that 1/10 of updates, I will calculate the longest block because I have to update the pred digest. So that update is crucial because at any moment, some other miner may create a new block. Now we have block miner index, which is the index of the miner who has proposed or generated the block. That's the block who gets the 8 coin incentive. And then there's a nonce, which is the number of calculated, which is the number that is calculated during the proof of work. You need to validate the nonce of every block once in a while to make sure no one has changed it. And to do this check, you need to make sure that the digest is less than the difficulty. Okay, that's how you don't validate the nonce directly. You basically generate the digest, so you make sure the digest is validated, and then nonce is valid if the digest is less than difficulty. Then you have timestamp, which is the time in which the block is generated. Obviously, the timestamp should be increasing from the very beginning, which is the genesis block, all the way to the most recently added block, or most recently generated block. All blocks are stored in a global list called blockchain, which is protected against race condition using a lock called blockchain lock. Let's take a look at that. That's your blockchain, and there's a blockchain lock here. Now, this blockchain gets pruned. You know what prune means? Pruning means, you remove the branches that are not the longest branch, that are not part of the longest branch. So once in a while, the blockchain gets pruned using the prune function, this one. And this is going to do a very simple operation. If you read it, you will understand this uses a dictionary of blocks to integers, integers to blocks, and it's prunes very quickly. This prune function will be called by the make transaction function, which is inside the initiate transaction, which is inside the miner run function. So every miner will prune the blockchain once in a while to make sure that the local copy of blockchain they have is correct. And it only contains the longest chain, I should say. Not correct. The blockchain only contains the longest chain. All right. Yeah, I said what function prune is. Then you have transaction structure. What is transaction structure? It's very similar to the Bitcoin. I mean, not very similar, but it's kind of a combination of Bitcoin. I mean, it's simpler than Bitcoin and Ethereum. It only has the very crucial pieces. Each transaction is an object of the class transaction containing the following elements. You have owner index, which is the ID or index of the miner who owns all the transactions input. We have both input and output, and all the inputs of a transaction should be owned by the same miner. Then you have timestamp, which is going to be the timestamp of the transaction. Timestamp always the output of the time ns function is in nanosecond. Then you have the list of all inputs, which I'll tell you what input is. There's another class called transaction input, which represents an input. This transaction input basically contains the block ID, the transaction ID, and output ID of the unspent output that we're gonna spend during this transaction input, during the transaction, right? So the input is a list of all inputs of the transaction, similar to the Bitcoin transaction input. A list is empty if and only if transaction represents the 8 NYTC mining incentives. So the only transaction that has an empty input list is going to be the mining incentive that a miner wins when it wins the puzzle of proof of work. Otherwise, the list is not empty and it's going to represent a list of objects initiated from the class transaction input, which is going to be a class containing 3 numbers. Block ID represents the block number of the block storing the transaction, outputting the unspent output. The transaction ID represents the index of the transaction in the list of transactions of the block specified by block ID. And output ID is basically the index of the unspent output in the list of outputs of the transaction identified by transaction ID. So using these 3 numbers, you can uniquely identify the output that is going to be spent using this transaction input. And what is outputs? Outputs is basically a list of outputs of the transactions. The list contains objects of class transaction output. What is transaction output? It's a class defined in the code. You can take a look at it. It has the following variables. One is called new owners index, which is going to be the new owner of the coins. It's going to be the index between 0 to the number of miners -1. And then there's an amount which specifies how many NYTPs are going to be transferred by this transaction output. And there's a spent Boolean. This Boolean is not going to be stored inside the blockchain. This is just a local Boolean that's we're going to assume that miners will keep so that they will find out which transaction output has not been spent yet. And this way we can easily find the unspent transaction outputs. The goal of this Boolean is only to simplify the local implementation of double spending avoidance policy by miners so that no miner can double spend some value accidentally. Of course, they can maliciously spend an output multiple times, but there exists a way to catch the cheaters who want to double spend an output and correct the blockchain. All right, then there's a signature that is going to be generated by the function RSA message sign with the private key of the miner who owns all of the transactions input. So the person who owns the transaction inputs will sign the transaction so that everyone knows that this transaction comes from someone who owns the inputs, right? So that transaction will be validated that way. And please note that the starter code explains everything, and also the starter code will generate, or I should say, initiate a bunch of transactions with a certain transaction rate, which is in once per second. If you look at my transaction rate here, it's a global variable set to 1. And I'll tell you how this specifies the rate of transactions. And that's basically specifies the speed of generating or initiating new transactions made by miners. Each miner generously distributes half of its balance evenly to other miners, just for fun, for seeing how the transactions will look like, and we create some action in the blockchain. And let me explain that. That's the last part I'm going to explain. And then after that, I'm going to talk about tasks 1, 2, and 3. So you see, I told you the miner run function. And I told you that in this if, which happens every 10th of a second, the miner is going to call the initiate transaction. And it's going to pass both index and the transaction rate. Let's look at the initiate transaction. in the initiate transaction, we're gonna first do this. The transaction rate divided by 10 is gonna give you a ratio. Subtract it from 1 and compare it with a random number between 0 and 1. If this is true, and the miner has enough balance, then the miner starts spending half of its balance. When do we have this condition set to true? It depends on the transaction rate. For example, if the transaction rate is 1, which is a default value, this happens every 10 times. So every 10 times that we call the transaction, initiate transaction, this will become true. And if in that time, the miner has some money to spend, then it spends it. How does miner spend its half of its balance? We're gonna pick the receivers from all the miners except the sender. So miner picks every other miner as the receiver of the fund. It calculates the value of the fund that has to be transferred, which is going to be the balance of miner divided by 2 times the number of receivers. So that means we're going to evenly distribute the money, and then it's going to do the it's going to call the make transaction for every sender, for the sender and all the receivers with the value that is given. If that make transaction returns true, we are going to subtract the whole amount from the miner's balance. And everything here from beginning to the end is inside the balance lock of the miner, so that we can avoid all the race conditions. Now, let's take a look at the make transaction. The make transaction basically gets a sender, a list of receivers, and it distributes this amount to all of the receivers. I explained that here, you can see it. How does it work? Basically, we are going to create a list of transaction outputs for the same amount that we're gonna distribute, and J is gonna be one of the receivers. So we first create a list of outputs. Then we are going to calculate the total amount that we're going to spend. Then we are going to acquire the lock of both the blockchain. We're going to prune the blockchain to make sure no blocks are invalid, and no blocks are outside of the longest chain. Then we are going to create a set called spend outs, and then we're going to go over all the blocks and all the transaction in every block and all the outputs in every transaction of every block. So basically, we're going to go through every output, and we're going to check the following. If the output new owner is this equal to sender, so that means if the output is owned by the sender, and the output hasn't been spent before, and we still need some money for the current transaction, we are going to spend that output by setting the spent equal to true, adding the output to the spent outs, appending the transaction input of BT and O, which are the addresses of this output, to the inputs of the upcoming transaction, and we are going to subtract the output amount from the total amount. And we're going to do this as long as the total is positive. When the total becomes 0, if total never gets 0 or negative, then we can just print an error saying you have insufficient fund, and then this can happen. So if that happens, you need to unspend or undo what you did before. So you need to set the spent of those spent outs to false, and then that would be it. Just return false. That means you didn't have enough fund to fund the transaction. That's possible because while the sender wants to generously spend half of its balance, someone may enforce a transaction, spending a lot of money from that sender, and then the sender won't have enough balance to give it out to other transactions. So that's very possible. But if it happens, nothing bad is going to happen, because we're going to undo all the spent outputs. And then if the total becomes negative, that means there is some change. So the change should goes back to the sender's wallet. How does it work? Basically, we're going to create a transaction with the negative total amount going back to the sender. So the sender pays itself the change, and the balance will be increased by the total, and then the transaction will finally get made with the sender, with the ins and with the outs, and then we are going to make the transaction happen by sending the transaction. When you send the transaction, it's going to call this function, which is going to add the transaction to the transaction pool. This transaction has been added to the pool, but the money is going to be given to the recipients of the transaction, not now, after the transaction is included in one of the blocks in the blockchain. So it's a complex story, but that's how it works. That's, you know, blockchain. I mean, the Bitcoin cannot, like the coin cannot be implemented easier than this. I try to minimize it and remove a lot of complexities from it. Still, it looks complex. Anyways, that's how you initiate the transactions. And when you initiate all the transactions, the balances will be updated as well. I talked about that, the balance of sender. And later, when the miner finds a block and the proposed block gets accepted, that's when we're going to go to each recipient of that fund and increase their balance. So the balance increase happens here within the successful mining if of the miner. So the money will be transferred right here in line 240. Okay, so that's the whole code. So let's talk about the actual three steps that you need, three tasks that you need to do. Run the given code for each of the following cases. Scenario 1 is this, so don't change anything, just run it. Scenario 2, change these 4 values and run it again. Scenario 3, make more changes and run it again. Of course, scenario 3 will take you the longest, but let me just run this so you can see how it will look like. So as you see, it starts mining, and whenever a new block is generated, it just gives you a new block. Whenever a transaction is sent, it's going to give you a transaction sent. And this is basically all the details of each transaction. And things are going to go forward until 20 new blocks generated, messages appear on the screen. And at the end, it's going to show you the balances of all the miners, followed by the remaining balance in the pool of all transactions, which most likely is going to be 0, but might be non-zero as well. If it's non-zero, it's not wrong. And yeah, that's pretty much what it does. And after doing this, which is gonna run the current version, it's going to ask you, it asks you in this next task to modify the given code so that each transaction has a transaction fee deducted from the owner's balance. You can do this in many different ways. The fee must be 2% of the transaction's total output. So when the owner wants to give out half of its balance to others, that's going to generate a transaction, right? And if the amount is half of its balance, so the transaction fee would be 1% of its balance, right? Because 2% of half of a balance is 1% of the original balance. So the miner who wants to be generous and give half of its balance to everyone else has to incur this 1% or 2% of transaction total output, or 1% of the actual balance out, or has to give this out. Who's going to get the fee? The miner who will add this transaction into a block. So in order to manage the transaction fees, whenever the block is going to be added to the blockchain, which is here in this part, when you do this is when you add the proposed block to the blockchain, you need to go over all these transactions and give the transaction fee to the miner, or add the balance of the miner by the transaction fee, right? And this transaction fee has to be deducted from the person who makes the transaction, the balance of the miner who makes the transaction at the very beginning. So inside the initiate transactions, when you initiate this transaction, the way I explained it, which is basically here, which is going to be inside make transaction, which is going to be here. You need to consider that transaction fee as well, right? So the sender will have to spend a little bit of its balance for the transaction fee. So you figure it out. It's not a big deal. One way to do it is right here. When I deduct the balance, I deduct the amount of the whole transaction from the balance of the sender. Here I can incur the cost of transaction fee in line 179. But there are minor details that you may want to take care of when you do that. Make sure everything is working. You can test it after you make any changes and see if the fees are deducted properly. In order to do the test, don't test your test bench with big numbers. For example, 2 miners is enough, and basically 2 blocks per miner is enough, and difficulty doesn't need to be harder than this. So try it with small values and see if the transaction fees are deducted properly or not. It's not going to be a big deal. You just need to manage it yourself. I don't want to explain how to do it because I want you to go over the details and figure it out, because that's an important concept. Next part, implement and use a function called verify all blocks, which is called periodically every 5 seconds by each miner, assuring the following. By the way, when I say every 5 seconds, you need to do it in a similar way that I did every 1/10 of a second updates. Let me show you. Do you remember this part, right? Where I said we're going to update every 1/10 of a second. How do I ensure that this happens every 1/10 of a second? Remember the time NS basically gives you the time in nanosecond. You get the start time, subtract it from the current time. That's going to give you a period. That's going to give you a time window, a time interval. In order to measure the length of the time interval, I divide it by 1,000,000 to convert this to millisecond. And then I compare that with 100 milliseconds, right? That means what? 100 milliseconds is 1/10 of a second. So I will first calculate the window that has passed since the last operation and convert it to millisecond. And then I said that should be greater than 100. And of course, every time the start time should be updated. The start time should be the current time, because you need to update the start time after every update. So this is for the update of every 10th of a second. The question asks you to do the update every 5 seconds. You need to do similar task, right? The similar operation. Instead of greater than 100, you need to say greater than 5,000, because 5 seconds is 5,000 milliseconds. And to verify all blocks, each block has to check the validity of the digest. How does it work? Basically, you need to call the SHA-256 on the block except the digest to see if that is going to be equal to digest. Let me show you the block constructor again, so I can exactly tell you what you need to do. You see this constructor of block, when it calculates the digest, you need to assure that the self.digest is the same value. And as you see, in order to calculate the digest, I call the str function. An str function basically gives me the string representation of the block except the digest. So as you see, this digest does not appear in the string representation. And that's important, because you can't have digest calculated by its own representation. That's nonsense. So so everything is correct. Just make sure that just run this again and make sure that digest equals to that value. And the next one, when it says each block has a valid nonce, that means the digest should be less than the difficulty. So you don't check the nonce directly, you check it by comparing digest and difficulty. Each block has a valid pred digest. You need to just check the blockchain and make sure that the pred digests are the real digests. And when you're validating the blocks, don't start from the end and go back to the beginning. Start from the genesis block and go forward, right? So whenever you want to validate the blocks, start from the very beginning, right? Then you have the next check, which is each transaction of each block has to have a valid signature. Verifying signature is done by a function which you can find here, line 79. I want to explain more. Each transaction of each block has a valid signature. I just explained that. Each input of each transaction of each block is owned by the miner who signed the transaction. That you can check easily as well. Basically, the inputs have owners, so you will be able to. No. Let me explain it again. Yeah, the inputs are referring. Each input refers to the output, and the output has owner. So that way you can check to see each input of each transaction of each block is owned by the miner who signs it. That can be checked. Just need to trace the input back to its corresponding output and then find out the index of that output. Then it says each output of each transaction of each block has been spent at most once. So there's no double spending. You need to double check that. Although there's a spent Boolean, but that's not stored in the stored in the blockchain, and I can show you why. Because each block stores these, and among these you have a list of transactions, and inside each transaction, what we store is the inputs and the outputs, and the spent, which was part of the output, is not part of the string representation. So the spent is not going to be stored in the blockchain. that I said this because for making this check, you're not able to do the spend, you're not able to check the spend because the spend is a Boolean that is not stored in the blockchain. You need to do the check in a different way. I will basically, you can do it in many ways. The worst case scenario is n squared, where n is the number of outputs, but try to come up with a better idea. If you can use a dictionary or a hash set, that's going to be the best way. But otherwise, you can do it in a brute force fashion and make sure that the output of each transaction of each block has been spent at most once. You can do it brute force. This is not an algorithm. And that basically means the output appears in the input of no or exactly one later transaction. Okay, and you need to run the program with the given values in scenario 1 for this part, and report whether or not the blocks are verified by all miners throughout the execution of your program. And you do that. Did I talk about? Yeah, I talked about question 2 as well. In question 2, after you do the change, you need to run it and run all 3 scenarios, and you need to observe the output.